Now it's time for really exciting stuff. We are going to use Laplace transforms to find derivatives and later on integrals. That's really where the power of the Laplace transform is at its fullest. And I hope you'll agree with me just in a moment. So what we want to do is to use Laplace transform to find a Laplace transform of a derivative of a function, or even a second derivative of a function. And you'll see that the result will be much simpler than the derivative. Let's use the definition. So by definition, a Laplace transform of a derivative is an integral of the derivative with respect to some exponential. And use integration by parts to take the exponential outside, and then if we compute these limits and that part literally means a limit at time getting large, or rather infinite, we put inside f of t times. So that is what is meant here. So as time grows larger, larger and larger, the terms really disappears, because exponential, as you remember, drops like that as time progresses. Right? So it becomes smaller, smaller and smaller. And providing that our function is reasonably well behaved, so it doesn't grow faster than these drops, then this term will be zero. And for most practical applications, that's the case. That's true. And the other limit, we just put 0. So we plug in times equals 0 for the function multiplied by exponential at the power of 0, which is 1. And we have the original integral on the right, as last term. So putting that together, we recognize that that integral is nothing else than a Laplace transform of a function times s, and we have also that term. So we've found an expression for the Laplace transform of a derivative. And note that all you have to do is to multiply s by the Laplace transform of a function and subtract the value of that function at 0. There's nothing else to do. So if you know Laplace transform of a function, you can compute its derivative in a second. So that is, again, just to summarize, that's a very important result. And we can even do more than that. We can find a derivative, sorry, Laplace transform of a second derivative. So let's find a Laplace transform of a second derivative, which is, in fact, is a derivative of a derivative, right? So it's a derivative of the df over dt, if you remember from previous course unit. So what we do now is just apply this rule again. So there's a derivative of a derivative. And if we apply that rule, as we've seen previously, treating this as effectively another function, we can use this formula, which we've seen, that Laplace transform of a derivative, let's say of different function dg over dt, is s minus 0. And here g is the derivative of f. So by doing that trick, we can find, and I also know that there's notation for derivative as that, so we can find the Laplace transform of a second order derivative. And if I simplify it a little bit by using the actual definition, so that Laplace transform of the first derivative of a function, rather property, not exactly definition, property, is s times f of s minus f at 0, f bar, right? So using that property, we can get this expression, and simplifying it one step further, we get a final expression. So that is a Laplace transform of a second order derivative. So in this case, we take s squared multiplied by the Laplace transform and subtract s times function evaluated at 0 and minus its derivative evaluated at 0. So that's this just in more usual notation. So in this case, if you know the derivative of a function and its function at point 0, and you know its Laplace transform, you immediately know its Laplace transform is derivative anywhere. So that is two very important properties of a derivative, which I want you to remember and understand. So to compute this, you need to know the Laplace transform of the function and its value at 0 for the first order, and also its derivative for the second order. And that will come very, very handy. Even if it's not obvious now, you'll see it once we come to applications, such as the RLC circuit. But let's just go and look at the example. Let's prove that this is actually true for a specific function. Let's prove it for a function sine plus a square function. To do it, we just compute first the left-hand side and then the right-hand side. So what we want to prove is that indeed it's true that a Laplace transform of a derivative of df over dt is the s times Laplace transform of that function minus its value at 0. So first, we just compute the left-hand side. And then we compare it to the right-hand side. So we look at the derivative of a function, which is 2 cosine 2t plus 2t. So just to remind you, the initial function was f of t is sine 2t plus t squared. That's why you get this derivative, like that. All right? And then we'll find the Laplace transform of the derivative. So we get a Laplace transform itself first, just to get ourselves warmed up. So the sine plus t squared, just use the tables, and you get this. And then you get the derivative. So 2 cosine plus 2t, so you get that, and these are just the constant factors, right? So use linearity and the tables. And then we want to compare it to the right-hand side. So we look, so just what we know that Laplace transform of f of t is 2s squared plus 4 plus 2 over s cubed, and we know that Laplace transform of its derivative is 2s over s squared plus 4 plus 2 over s squared. We did it directly, but let's check what right-hand side tells us. So right-hand side tells us that we want to compute s f bar over s, which is that. Minus function at point 0, and since our function f of t is sine 2t plus t squared, then we can just plug in that property directly into here, and also evaluate this function at 0. So if I do that, we'll see that we get s times 2 over s squared plus 4 plus 2 over s cubed, and we subtract this. We subtract from this the expression sine 2 times 0, which is 0, plus 0 squared, which is also 0. So in fact, the second expression is 0. So all we left is only the first, which can be simplified as 2s over s squared plus 4 plus 2 over s squared, because we have the cube and the factor which become inverse second power. And then by looking at this, you indeed see that this is nothing else than a Laplace transform of a derivative. So by inspection, we can see that indeed this right-hand side equals to the left-hand side. And that is what we was asked to demonstrate.